Good morning, peeps. How are we doing?
Hey Nick, just a quick clarification.
Yeah.
Um, so for that homework, chapter 12B,
Yep.
um, maybe I just missed something during a lecture, but it says that there's the second exam on
Oh,
Friday. I guess
I
that's just
erased. I just noticed that this morning. That was a leftover from a previous year. Totally not true. I erased it this morning. So if you go back and reload the assignment, it will not say that anymore. So full marks to you for noticing. Apologies for having left it there. And if I freaked anybody out, I'm very, very sorry. I did not. Yeah, that was just bad on me.
okay. Sounds good.
Other random things that I missed or otherwise messed up or just wasn't clear about? Okay, well, let us commence. Um, so there are 2 weeks of classes left. Holy moly, I don't know how that happened. So we have nearly survived the online version of the world, and that's really awesome. Yay, team. And you folks have been really good. So thank you very much for your patience and your cooperation. Um, the exercise 12B, it had been due Thursday night. I moved that to Friday night, so we'd have class time Friday to talk about stuff. There's a coin problem. We've gone over that. So you know that they take a while to write up because there's a lot to say. So you should definitely get on the coin problem. We will start recursive definitions today, which is what is important for the other problems on the assignment. So we'll try to get things sort of ready today so that you can be working on that. I mean, you can always just read the book and be working on it anyway, but we'll try to cover that in lecture today. And then I think we'll finish chapter 12 maybe today. Hopefully, if we get lucky, might dribble a little bit into Wednesday. Then we'll do chapter 10 basically for the rest of the semester. And that'll probably be the last thing we cover in the book. So there's a couple of pieces that we have historically covered, but we're just not going to get there, and that's going to be okay. I will probably hand out the take-home final a week from Wednesday, so middle of next week, and then we'll have Wednesday and Friday to talk about it. It'll be due at the end of the scheduled finals period, which is Tuesday afternoon. I will try to set up some office hours on Monday of finals week, so that if people have questions, you can sort of set up a meeting and we can chat about how the exam's going, and I can try to give you hints and tips and stuff like that. I just finished a pile of exams for another class that was even more behind than we are for you, if that's believable. And so your exams are next on the list. So I'm going to try very hard to get those done this week, hopefully by Friday. We'll see how that goes, but that's the plan, so that you'll get those soon. Because I don't know how long it's going to take for sure, one thing I'm going to do is, so I grade them sort of one problem at a time, or one section of the exam at a time. And normally I would hide all the grades until everything's done. But in order for you to get feedback kind of as I go through things, I'm probably going to post grades for sections as I finish them, which means when you first get a notification from Canvas, it will say that you've got like a 8% on the exam because I will have just graded one problem. And everybody will freak out and be like, I'm failing. And it's like, no, you're not failing. I haven't graded most of the exam. So when you get that notification from Canvas, don't panic. Go look at what the grade actually is on Canvas, and you'll see that most of the problems are still ungraded. And that, I've done a thing. And then as I go through, I think Canvas is going to send you a notification every time I do a problem. So you'll end up getting a bunch of notifications from Canvas as I sort of work through the exam. But that way you can kind of see how you're doing instead of having to wait until the very end to see how you did. Because I'm trying to figure out how to get you feedback as quickly as possible. Questions about anything before we finish up induction proofs?
This isn't like really necessarily about the class, but do you know when we get our money back?
I have no clue. I am not connected to that part of the universe, so I really don't have the foggiest, I'm afraid. I would guess that One Stop would be the place to ask, unless somebody here has some magic knowledge on this front.
No, I was just curious if you knew anything.
No, not a clue. It's one of these moments where, since I'm not a student, there's just things I don't know anything about because they don't need to be telling us that, and even if they did, we probably wouldn't pay attention. So they've learned to ignore us. Other questions that I can be completely unhelpful with? Okay, let's do this thing. Whiteboard. And come here. There we go. Yeah, you can do it. So one last little thing on the coin business, and then we'll be done with that. So I'm going to clean it, sort of tidy up the coin. But we're still in green. Let's make that black. So tidy up coin. And what I want to do is just illustrate how this would actually play out in a computational way. So the key thing from the proof, and I don't have time to sort of repeat all the proof stuff, but if you've got questions about any of it, definitely feel free to ask because it's important for that one homework assignment. And I think it does really pull together so much of what we've been doing this semester that it's a really good thing to ask questions about. But there were two versions of one that we played with. We had one was -2 times 3 plus 1 times 7. So we could remove 2 3-cent coins and add a 7-cent coin. And that we could only use if p hat was at least 2. And then there was also one was 3 times, sorry, that would have been to be consistent with what I did over there. It would be 5 times 3 plus -2 times 7. And that was for when q hat was at least 2. So we could go forward by 1 by trading 2 3s for a 7, or give away 2 7s and get 5 3s. And we can actually see this play out if we think about a table like this, where we have like 12, 13, 14, 15, and I'm not sure how far we'll go, we'll see. But if we had P and Q, and 3 times P plus 7 times Q, we started off with 4 and 0. So you have 12 plus 0 gives us 12. And because P is at least 2, in this case, we can trade away a pair of 3s. So we're left with 2 3s and get a 7. So we're getting rid of 2 3s and gaining a 7. And that gives us 6 plus 7, which is indeed 13. So we can use this method to, if I know how to make 12, then this tells me how to make 13. I don't have to like guess and flail around. And now similarly, well, I've got at least 2 3s, so I can again drop that to 0, and add a 7. And so I get 0 plus 14. That's 14. That's awesome. Now, I can't do that again here because I've run out of 2s. Oops, sorry, that should have been a 2 there. Erase. Boink, boink, boink. Come on, go away. There we go. So that should have been a 2. So I can't, to get from 14 to 15, I can't trade out 3s because I don't have any left. But I can use my other rule and trade out both 7s and get 5 3s. And now I've got 15 plus 0. Okay. And then 16, I'll trade out a pair of 3s for a 7. And so I get 3 times 3 is 9. Oh, man, I said 7 again. Boink. Should have been 1. My apologies. 1. So that'd be 3 times 3 is 9. Plus 1 times 7 is 7. And 9 plus 7 is indeed 16. Okay, and then I could do one more. I can trade out a pair of these and I get a 1 and I add another 7. So I get 1 times 3 is 3 plus 14, and that is 17. So I can, in an entirely mechanical computational way, work myself forward once I have a starting point. That the calculations we did give me a mechanism for just cranking out answers as far as we want to go. Okay, and so far, there's always ever only been one option. When we had 2 7s, there weren't enough 3s to use. When we had 2 7s, there weren't enough 3s to use. We can, in certain circumstances, end up with situations where we might be able to use either option. So 20, if we continue doing this, would turn out to be 2 and 2, a pair of 3s and a pair of 7s makes 20. And now at this point, we could do 2 options. We could either trade 2 3s, for a 7, or we could trade 2 7s for 5 3s. Oh, sorry, and there were already 2 3s there, man. So we'd trade out 2 7s, so we'd be at 0 here. Oh, sorry, having problems with my thing here. So 2 0s, 2 7s, we'd lose both of those. And we gain 5 3s, that would be 7 3s, because we'd have 2 from before. And both of these give us 21, because we have 0 plus 3 times 7 is 21, and 7 times 3 is 21, plus 0. So there are 2 ways, both rules apply, and that's fine. Because we don't need, all we need is a way. It's okay if there's actually more than one way to solve the problem. But, regardless, we can use this to sort of compute our way down to whatever value we want. If somebody's like, make 112, we could grind through this till we got to 112 or 1,012. Wouldn't be fun, right? 1,012 would be a long way, but with a computer, actually, 1,000,000 steps wouldn't be that big a deal these days. So we can compute our way to finding out any solution to sets of 3 coins and 7 coins for any number bigger than 12. So questions about that? And that will be the end of the coin thing. Unless there are questions about it, which is totally cool if there are. Going, and gone. Okay. So now we're going to move on to the last part of chapter 12 that we're actually going to cover, which is the recursive definitions. And these are either called recursive or inductive definitions. Both terms are used. And if you've if you took 1301 last semester in Racket, we did recursive definitions all the time. And if you're in 1201 this semester, you probably are doing or have done some recursive definitions there, although probably not quite as intensively as the folks in 1301, but it should be fine. And if you've not had either, that should also be fine. The basic idea is not all that complicated. And as an example, let's think about factorial, one of the classic examples of a recursive definition. So factorial is typically written with an exclamation mark. So n, that's read n factorial. And n factorial is 1 times 2 times 3 times ... times n. And if we wanted to do this in terms of quantifications, this would be, the product over I, 1 at most, I at most, n, I. Okay. Now, and that actually gives us a definition of factorial that doesn't involve the dreaded ... dots. But we could also do a recursive definition. So we could say 0 factorial is 1. And that maybe seems a little weird. Notice it's consistent with this. If we put 0 in for n, we get empty range, and the identity of multiplication is 1. So it makes sense, if nothing else, from this over here. And then n factorial is n times n minus 1 factorial for n at least 1. And so essentially what we're doing here is we're saying that n factorial is everything up to n times n. So this is kind of that piece there, and this is this piece here. And this might seem a bit like circular logic, but because we're always moving down, we're going from 7 factorial to 6 factorial, and 6 factorial to 5 factorial, and we sort of walk our way down until we hit the bottom, and that's where the base case kicks in. This actually works. This is legit. Questions about this definition and this idea? Another common example is exponentiation, where if we think of a to the n as a times a times a times ... a n times, which is, again, we could write as a quantification. But now instead of multiplying I over and over again, we multiply a over and over again. So a times a times a this many times. So we could define exponentiation that way, but we could also say that a to the 0 is 1, and a to the n is a times a to the n minus 1 for n at least 1. Okay, so we can, a to the 5th is, let's say 2 to the 5th is 2 times 2 to the 4th, which is 2 times 2 to the 3rd, which is 2 times 2 squared, and we'll eventually get down to 1, and so it just becomes a way of writing this, essentially. Okay, questions about that? Now we can do induction proofs on these things, which is actually pretty cool. So let's see, I think I can maybe make it fit here. I'm going to change colors though, so it's clear that where the proof is and where the other random definition stuff is. So I could claim that a to the m times a to the n equals a to the m plus n for n at least 0. So this is a common fact about exponents that you may dimly remember from some point in high school. But if you have thing to the m times thing to the n, you get to add the exponents if you multiply the powers. And we can prove this by induction on n. And people are often sort of befuddled on this problem because there's a, m, and n. It's like there's too many letters, and what are we doing? And all we're inducting on in this case is n. We're going to just treat a and m like they're magic things that came from outside. It's similar to the r in the, well, r and x and y in those two problems from the homework. They're just numbers that come from somewhere else, and we don't really have to care what they are or anything about them. So we'll just do induction on n. And so the base case is going to be n equals 0. Because, and we know it's 0 because this was true. This gave us a definition of exponentiation for all natural numbers, so starting at 0. So we'll need to start at 0 here as well. And I'm going to squeeze this in on the bottom here. So this would be a m times a to the 0 equals a to the m plus 0, which is, we'll say by algebra, a to the m times, oh, and this is actually the definition of, and definition of exponent. So this is 1 by that piece up there, and then m plus 0 is m, and that's true by arithmetic. Right? We know that multiplying by 1 gets us back to where we started from. So that sorts out the base case. Now I flew through that really fast, so feel free to like raise a white flag and be like, slow down, explain yourself. It's all totally obvious. Cool. Now the induction step. Right, and remember the induction step is P of n implies P of n plus 1, or the simplified induction step. Oops, that should just be a plus. And so we're going to assume a to the m times a to the n equals a to the m plus n, and prove a to the m times a to the n plus 1 equals a to the m plus n plus 1 for n at least 0. Boom. Are we cool with the setup? Questions about sort of what I'm doing here? So I'm just assuming this is true for n, and I'm proving it's true for n plus 1. Right. This is pretty much exactly the same setup as before, but now instead of like split off term or something like that, we'll use the definition of exponents to simplify this expression. Okay, So let's take the whole thing and we can use this definition of exponents twice to rewrite the n plus 1 as n. So here this says n goes to n minus 1, so we can also write that as n plus 1 goes to n. And we'll do the same thing over here. Oops, sorry. I needed to put the a in the front. A times a to the m plus n. So I've used that to peel the plus 1 off of the front, or the back, sorry, of the exponent there. And I thought that was me, actually, that made all those backslashes. So yay for your cat. So does this make sense? This is where we would have used something like split off term in like the 12.4 problems. But now, instead of using split off term, we're using the definition, the recursive definition, to rewrite this as something like that. And that's like the really important step here. So if you got questions or confusion about this, this would be a great thing to ask questions about.
I'm just kind of confused because it seems like we're using what we're trying to prove.
Yeah, well, you are. I know it feels that way, but this is the definition, and we're proving a property of that definition. So we're saying, let's define it this way. Now, once we've defined it, what do we know about it? And one of the things that we know about it is this. And induction says, how do we prove something like that? Well, let's assume that it's true for n and show that it's true for n plus 1. So we're assuming this. This is what it means to assume this is true for n. And then we're proving that it's true for n plus 1. And to get from the n plus 1 back to the n, we're going to use our definition here, which lets us go from n to n minus 1. Or if we want to think about it, an alternate way to write this would be to say a to the n plus 1 equals a times a to the n for n at least 0. Like these two things are equivalent. And so I'm using a to the n plus 1 is a times a to the n, using that rule. And a to the blah plus 1 is a times a to the blah, using that rule again. And I know it feels like you're using what you're trying to prove, but you're not, because here you're always going from a bigger number to a smaller number until you get down to the bottom. And then induction, you're going the other way. You're starting at the small thing and showing that you can go up to the next one. So you're always going the same direction.
Yeah.
Go ahead.
That makes sense now. I'm
Okay.
just confused because they seem like they're like almost the exact same thing, but
Yeah, it does. I totally get that. So does that help?
Yes, thank you.
Not a problem. So then, well, if I need to use the induction hypothesis, which says that am times a to the n is a to the m plus n. Well, I've got an m plus n here, and I have an a to the m and a to the n. So if I rearrange things using associativity and symmetry of multiplication, I can rewrite this as a times a to the m times a to the n equals a times a to the m plus n. And then that, I can use the induction hypothesis I'm getting really close to the bottom. I apologize. I'll say a to the m times a to the n is a to the m plus n. And then that's what I have over here. And I'm done. So this finishes the induction step because these two sides are clearly equal. And then I've done the base case, I've done the induction step, so I've done the whole proof by induction. So the induction proofs with recursive definitions look a lot like induction proofs, other induction proofs, but where in other cases we might use split off term or similar because we're often doing proofs with quantifications. Here we're using a recursive definition, and so where we would have possibly used split off term here, we use the recursive definition instead of split off term, and then the rest of it's very similar. You do some work and eventually you get to use the induction hypothesis. So, questions about that? So there's your basic proof by induction using recursive definition, where we'll now go on to the Fibonacci numbers, which is actually what the homework problems are. And they're a slightly more complicated version of the same thing. And they're a nice example of why strong induction is sometimes important, which we sort of glossed over earlier, but now we'll have to actually deal with it a little bit. Questions before we make a new slide? Here, I'll change my color back to black. Okay, new slide. Fibonacci numbers. Oh man, I am doing terribles. So Fibonacci numbers actually are an old idea. The Fibonacci family did a lot of important math in I think the 1400s, a long time ago. And they came up with this idea as a way of modeling population growth, actually. And the sequence is pretty straightforward. You have 0, 1, and then after 1, every number is the sum of the previous two numbers. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 8 plus 5 is 13, 21, 34, 55, dot, 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 dot. So that's the basic sequence, not too complicated. It is often defined recursively. So there is a very simple recursive definition. It says f of 0 is 0, f of 1 is 1, and f of n equals f of n minus 1 plus f of n minus 2 for n at least 2. This is sometimes also written as f of n plus 2 equals f of n plus f of n minus 1 for n at least 0. And again, these two things are essentially equivalent. So it doesn't really matter which one you want to use. Okay. And it turns out, weirdly enough, Fibonacci numbers come up all over the place. They turn out to be very important in modeling a bunch of different processes in biology. Turns out that plants do weird things with Fibonacci numbers that you wouldn't have really expected. There are computer science things like Fibonacci heaps that use this basic idea. We use Fibonacci numbers as a set of values for estimating the difficulty of stories. It turns out that they There's nothing mathematically special there, but it turns out they just work well in practice as a set of values to choose from. So Fibonacci numbers come up a lot, and they're pretty cool. You can do some nifty things with Fibonacci numbers. And if we want to prove things about Fibonacci numbers, we typically do this using induction, okay? So I'm going to do an example. Actually, there are questions about the Fibonacci numbers before we launch into an example. We're going to do exercise 9.20, which says that, I'm going to do this out here because I'm just trying to save some space, that Fn is less than 2 to the n for n at least 0. And if you look in the book, there's actually a typo in the book in this exercise. They have a less than or equal to 0 here. Definitely not true. Needs to be greater than or equal to 0. And so we're going to do a proof by induction on n. So this is basically P of n. Now the tricky part here is the recursive definition only works for n greater than or equal to 2, because if we had a 1 here, this part would go boom, right? We need f of minus 1. Now we could define f of minus 1 if we wanted to get fancy, but that would just move the problem to another place. We still have this issue that to do something with f of n, we need to use the previous 2 values, not the previous 1 value. So if we flip back to the previous slide, a to the n only depended on the immediately previous value. It didn't depend on n minus 2 or n minus 3 or anything before that. And if we go all the way back to like the 12.4 problems in the book, split off term, we could take the n plus 1 case and turn it into an n case with split off term. And that's as far as we ever had to go. We didn't have to split n into n minus 1 into n minus 2. We could just stop at n and be done. But with Fibonacci numbers, because we need the previous 2 pieces, we're going to have to actually care about 2 base cases. We can't just do it for 0. We're going to need to show it for both 0 and 1. That's a little weird, and not like what we've been seeing before. So because the recursive definition for f of n only works for n at least 2, we need to prove base cases for n equals 0 and n equals 1, right? Because we want this to be true for everything 0 and up. We can't use the recursive case until we get to 2. So we're stuck kind of doing it by hand, as it were, for 0 and 1. We need to do both of those before we can actually get into the induction part of the program. Does that make sense? And if you're fuzzy on this, the important takeaway as a practical matter is when you're doing induction proofs on Fibonacci numbers, you almost always have to do 2 base cases, 1 for 0 and 1 for 1. But it's almost always 2 base cases. And if this had been for n at least 3, the 2 base cases would have been 3 and 4, probably. But we almost always need 2 base cases. So let's do one of them. And so we put in 0 for everywhere. We have f of 0 less than 2 to the 0, which is by definition of f0 and rules of exponents. F of 0 is 0. 2 to the 0 is 1. And that's true. So we're happy with that base case. Does that make sense? I mean, it's a really simple base case. And then the other base case will be equally simple. So we have f of 1 less than 2 to the 1, which is by the definition of f of 1 and exponents again. F of 1 is 1. 2 to the 1 is 2. And that's also true. Whee! And there's our base cases. Questions? Now we get to the fun part. So we have the induction step. And I'm going to lay out some things about the induction step here, and then we'll actually do it on the next slide. Now, there are two ways to think about this. The first is full strong induction, like discussed in the book and that we talked about briefly last week, where instead of just proving the thing before, you assume everything before. And so in this case, that would look like for all I, for all natural I, where I is less than n, we'll assume f of I is less than 2 to the I, and that will prove P of n. So basically, we're not just assuming the immediately previous one. We're going to assume everything before and then show that it's true. A simpler version, which works fine for the Fibonacci numbers, because you almost always don't need all of them, you just need the previous two, is to assume f of n minus 2 less than 2 to the n minus 2, and f of n minus 1 less than 2 to the n minus 1, and show that that is f of n less than 2 to the n for n at least 2. So B here is a subset of A because it's just, it's included in this quantifier, but it's just the last two instead of everything. So if we were doing, I don't know, like f of 100, this would be f of 0 up through f of 99. And here we're like, we just need 98 and 99. We don't need f of 57 and f of 23 and f of 2. And I will use this, and I would probably encourage you to use this for the exercises in the book, but you could always fall back and have this if you found that you needed more than just the previous two for a proof that you were doing. Does this make sense? Questions? So the form, when we get to the next page, is we're going to assume this, and prove that. Okay? So just like in other induction proofs where we assume the earlier versions were true and we proved the later version. Here we're assuming these two things are true, and we're saying, can we use those two facts to give ourselves this? And if we think about the stepping stone example, where before we were going from 0 to 1 and 1 to 2 and 2 to 3 and 3 to 4, now we're using pairs of things. So we're using these two to get to there, and these two to get to there. So we're using the two previous ones to get to the next one, because the one before is not enough. We need a little more information. And strong induction says, you can use everybody from before, but we don't need that much. We don't need to get that excited. So on the next slide, I'm going to do the induction step using form B here. Questions before we go ahead and make the next slide? Okay. Let's see. Then next slide. Oh, I think I made two. Yeah, I did. Got excited there. So we're doing the induction step. So we're going to assume a bunch of things. We're going to assume that n is at least 2, that f of n minus 2 less than 2 to the n minus 2, and f of n minus 1 less than 2 to the n minus 1. Okay? With me so far? Our goal then is to prove f of n less than 2 to the n. Okay? Let's do it. So I'm actually going to start with the f of n. For inequality proofs like this with Fibonacci numbers, and one of your homework assignments is an inequality proof like this, it's probably simpler to start with the side that has Fibonacci numbers in it, because then you can just use the definition of Fibonacci numbers to open that up, and hopefully then useful things will occur. So I'm going to start by doing exactly that. I'm going to say that this is, by definition of Fibonacci, and the assumption that n is at least 2, because we can't do this next step unless we know that n is at least 2. Okay, so f of n is that. It's the sum of the two previous ones, and we know there are two previous ones because we're assuming that n is at least 2 here. Now, these match up our assumptions rather nicely. So we could say this is less than, by our induction hypothesis, two to the n minus 2 plus 2 to the n minus 1. So this is less than this, and this is less than that. So the sum of these is less than the sum of those. Okay? Are we cool with that? Questions about that step? Now the next part's going to look a bit like magic. However, it's useful magic for one of the problems that you're doing on the homework. So it's important to probably pay attention to what we're doing here and ask questions if you're like, I don't get it. So we've got this weird thing. We've got 2 to the n minus 2 plus 2 to the n minus 1. And we somehow want to like join those up and try to get to 2 to the n in the end, okay? And there's a bunch of different ways we can do this. I'm doing it in a way that's quite specific, because it's helpful on the homework problem that you have for Friday. So what I'm going to do here is I'm going to use, oops, not too many lines. This is just equals. I'm going to use rule of exponents. Negative numbers like this are division. So this is 2 to the n over 2 squared, and this is 2 to the n over 2. So if, in the same way that if we multiply, we add the exponents. If we divide, we subtract the exponents. So 2 to the n divided by 2 squared is 2 to the n minus 2. 2 to the n divided by 2 to the first is 2 to the n minus 1. So does this step make sense? Are people okay with that? Definitely holler if you like. Okay. Then I want a common denominator. So I'm going to use a little algebra so that I can have 2 to the n over 2 squared plus 2 times 2 to the n over 2 squared. So I wanted to get 2 squared on the bottom so I can join these up. So if I multiply both the top and the bottom by 2, then I get this. Okay. And now, now I can just do a little algebra to join. Now that I've got a common denominator, terrible. I can be 2 to the n plus 2 times 2 to the n over 2 squared. Now I've got a pair of 2 to the n's, so I can join those up. And I have 1 plus 2 times 2 to the n. So I've got 1 2 to the n plus 2 2 to the n's is 1 plus 2 times 2 to the n. Oops, 2 squared. Now we're almost there. Arithmetic. And I'm doing this perhaps in a little more gory detail than strictly necessary, but I want to try to be as helpful on the homework assignment as possible. So 1 plus 3 is 2. Now, at this point, I'm trying to get to 2 to the n here. And this is a 3 and this is a 4. Okay. And so there's a couple of ways I could do this. Actually, maybe a nice way to do this would have been, no, actually I'm going to do it again, try to make it match the homework assignment as well as I can. So this is using the fact that 3 is less than 4, which is 2 squared. This is, oh man, erase. Go back to a line. This is going to be less than, because 3 is less than 4, this is less than 4 times 2 to the n over 2 squared, which is, by arithmetic, 2 squared times 2 to the n over 2 squared, which is 2 to the n. By arithmetic. Whew. So I started with f of n. My spine is equal, less than, equal, 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 another less than, equal, equal. So f of n less than 2 to the n. And we're done. Yay. And that actually completes the whole induction proof, because that was the induction step. So we needed 2 base cases, but you only need the 1 induction step. You don't need 2 induction steps. You just need to assume more than you're used to assuming, because we need, after we use the inductive definition, the recursive definition, we need the induction step twice. So we need or the induction hypothesis twice. We need to have that is less than that, and we need that this is less than that. Right? So we're using both of these assumptions in this step. And then the rest of it's all this algebra. Okay. Questions about the structure? I've got a couple things to say about the algebra, but are there questions about the structure? So the other thing to note is when you do the problem in the book, and this is exercise, make sure I get the right exercise. Exercise 12.22, it's a less than or equal to actually problem similar to this, but it's gonna have a place where you end up with some negative, some exponents like this where you have n minus 4, for example. So when you get something like phi to the n minus 4, it's useful to write that as phi to the n over phi to the 4. Because then you can try to get a common denominator like I did here, join things up and do some factoring. So when you get things like this in the homework, splitting it up into things like that, rewriting it as fractions like this is probably very useful, he says, hinting broadly. Questions? Okay. It's also worth noting that 12.22 which is the one I was just talking about. Let me actually write the statement down. Says that phi to the n minus 2 equal or less than or equal to f of n for n at least 1. And the n at least 1 here means the base cases are n equals 1 and n equals 2. Not n equals 0 and n equals 1. Because this isn't true for n equals 0. So we start with 1 and 2, and then we assume, that it's true for n minus 2 and n minus 1 for n greater than or equal to 3, and go forward from there. Okay. And that's a thing that people often miss, is that this starts at 1 instead of at 0. Okay. And then the last big tip on this is this phi thing really tends to throw people. So I'm actually going to do even another color because I can. So phi is defined in the book. So you want to read page 224 to 220, I would say at least through 226. And that there's facts about this phi thing that matter here. And so what is phi? Phi is 1 plus square root of 5 over 2, which seems like a totally whack number. Like, why would anybody care about that? Turns out it also has a friend, phi hat, where hat here is not the same as hat in witness. It's just historically that's what people have used for this. And that's 1 minus square root of 5 over 2. And it turns out these two numbers have some pretty odd properties. In particular, we have that phi squared equals phi plus 1. and phi hat squared equals phi hat plus 1. Which is kind of an odd thing. That's clearly not going to be true for most numbers. If you square them, you don't go up by 1. But it turns out that both phi and phi hat have those properties. This will turn out to be really crucial in exercise 12.22, because when you do some factoring, you're going to end up with a phi plus 1, where I've got the 1 plus 2, you'll get a phi plus 1. And then you can rewrite that as phi squared using this fact from the book. And then you get some nice things happen, okay? So make sure you pay attention to these properties of phi and phi hat, because they matter for the homework problem, okay? Questions about that?
What exercise is that?
Exercise 12.22
Okay.
and 12.23. Both of these use these phi things and Fibonacci numbers.
All right.
Does that make sense?
Yep.
And then the remarkable thing, I mean, we're sort of working up to exercise 12.23, which I think is one of the most amazing facts in all of mathematics, which is that f of n is phi hat to the, or phi to the n minus phi hat to the n over square root of 5, where f of n is this sequence. Oops, that's a 2, 3, 5, 8, right? So that the Fibonacci sequence, every number in this sequence is this weird thing with square root of 5s and stuff in it to the n, minus another weird thing with square root of 5s in it to the n, divided by square root of 5. Like, it's not even obvious to me that that's an integer, not to mention this particular set of integers. I mean, this just seems to me to be entirely remarkable, that there would be something like this that would be true of any sequence, but certainly of an interesting sequence like this one. And you will, in the homework, actually prove that this is the case, right? Exercise 12.23 is to do this by induction on n. So you'll prove that this is true for all n. And that's pretty amazing, I think. I just think that's a remarkable fact, that this would turn out to do something interesting like this. Just boggles my mind every time I see it. And so you will, in this homework assignment, actually prove that this quite remarkable and unlikely thing is in fact true for all n at least 0, which makes me super happy. So questions about that? And you will need those properties from pages 224 to 226. You'll need those properties of phi and phi hat to make this work. Questions? Yeah, no, I played with that at some point earlier in my life, and I found it mostly confused people, so I haven't done it in a long time. Questions about anything? We got 2 minutes. I'm not going to like start something new at this point.
You mentioned earlier how there was a typo in the book.
Yes. That is, it doesn't affect you directly. Let's see if we, oh, it's here. The book has for n less than or equal to 0 on exercise 9.20 instead of greater than or equal to 0.
Okay.
You don't have to do this problem. I just did it. So It's not doesn't directly impact what you're doing, but it is an option. If you were looking at it, I didn't want you to become hopelessly confused, because that is definitely broken in the book. So, other questions? So I think all those little bells that just went off tell me that it's 10:20 and that's the end of class. So definitely take a stab at the homework. You have all the tools you need to do the homework that's due Friday now. So take a shot at it. Ask me questions in class, office hours, whatever, Slack, and I will see everybody Wednesday, and we'll start talking about chapter 10, actually, once we're done with whatever questions people have about chapter 12. So, cool. I will see everyone later. Ciao.